240 strange.
We have 240 because Jesse has a
Is
type
presenting. Okay.
Well,
I don't think that
it's all
changed.
today. Oh, dude, bad mood. Yeah, it's hard.
Yeah,
you can oil.
Oh,
You heard about that too? Yeah.
So before I start, just remember you're gonna have to do probably groups of 3 or 4 for going. There's gonna be some not labs, but some assignments that you'll have to work
Dude,
together.
don't worry, I'll take you home tonight.
The other thing is for the quiz today, it'll be do it at home quiz. I'll release the quiz around right after class. You have until Friday at 3 p.m. to finish it. If you do not get it into me by that time, it is a 0. Okay? Yes.
Okay, do you have like a cubby? Yes, he does.
You can put the stuff in the door,
In the door, not
in the door, in the mailbox, or you can submit it electronically.
Do you mind if we
I
hand
wasn't
it
able
to you
to
in
find
class?
your mailbox.
What?
Do you mind if we just hand it to you in class?
You can hand it to me in class as well.
Cubbies? Yeah, it's a cubby. Right next to Dr. Which cubby?
It probably says Kevin on it. Or
I just can't.
Kate Tom.
I swear. Somebody that's been here for 4 years and I just can't.
Okay, so any questions on that? No? Okay.
I must have missed the question. I just got signed in. Sorry.
What?
What did we just discuss? I just got signed in. Sorry.
Oh. I said there will be the quiz that will be released after class, a little bit after class. You have until Friday at 3 p.m. to finish it. Otherwise, it's a 0. Okay? You can submit it to the website. You can also email me. For those on campus, you can also put it in my mailbox or the slot on my door. Okay?
Slot over there.
If you slide it under my door, it will also be marked with a 0.
Kevin has to change his syllabus. No sliding under doors.
All right, that's enough. Let's see, where were we?
I think we're on page 8 or 9.
This one?
Next one. I think it was
Key alternating.
a lot.
Yeah. Because that's a lot.
Okay, I like DES, AES as an example of key alternating block ciphers and such ciphers. Each round first applies a diffusion achieving transformation operation, which may be a combination of linear and nonlinear steps. Incoming block, blah, 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 blah. DES is based on Feisel structure. AES is not. Substitution permutation network should be what AES is based off of. Okay, so AES is a byte-oriented cipher, which is really cool because it makes it easier to deal with. Okay, all operations on AES are purely byte level, which makes it really convenient and fast for software implementations of AES. Also makes it easier for us to do by hand. Assuming a 128-bit key, the key is also arranged in the form of a matrix. 4x4 bytes, as with the input block, the first word from the key fills the first column of the matrix, and so on. The 4 column words of the key matrix are expanded into a schedule of 44 words. Each round consumes 4 words from the key schedule. The key schedule basically has 44 4-byte words, which are generated with the expansion of the key. Okay, so encryption and decryption. The algorithm is actually not symmetrical. When we say a symmetric versus asymmetric encryption algorithm, or symmetric key versus asymmetric key, we're talking about the key, right? So asymmetric, generally when we say asymmetric encryption, we mean something like RSA, where there's a public and private key. Whereas the asymmetric encryption is a more, symmetric encryption, AES is still symmetric in the sense that it uses the same key to encrypt and decrypt. So here we have AES encryption and decryption. So for the most part, it's going in reverse, but some things are not exactly in the same order. Like, let's see, inverse, if we look, the encrypt, we have a subbytes over here, but then we do subbytes after. Shift rows is over here. So for the rounds, we do a sub byte, and then we do, so sub byte, shift row, mixed columns, right? Add round key. So down here when we decrypt, we do inverse shift rows, inverse sub bytes, and for add round key, and then inverse mixed columns. So it's not exactly one-to-one correspondence. It's not exactly go the reverse way to get the decryption, right? A little bit different. Okay, so AES stands for Advanced Encryption Standard. Affine transformation is a transformation consisting of multiplication of a matrix followed by the addition of a vector. An array is an enumerated collection of identical entities. A bit is a binary digit having a value of 0 or 1. I'm just thinking back to the other class when we were talking about logic type. Anyway, block is a sequence of binary bits that comprise the input, output, state, and round key. The length of the sequence is the number of bits it contains. Blocks are also interpreted as an array of bytes. Byte is defined as a group of 8 bits that is treated either as a single entity or as an array of 8 individual bits. We do have to define things like this, right? All this stuff is from a document called NIST FIPS 197. When we're dealing with standards for the government or military or aerospace applications or just industry-based, we do need to define even the most basic things over here. Does a byte really mean 8 bits? Not always. It didn't used to mean that, right? So we do need to define basic things like that. Did we skip one?
Yes.
Okay, so cipher. Again, cipher, you know what a cipher is, right? It's the output of the encryption algorithm. The cipher key is input to the algorithm along with just plain text, right? Plain text is just the data you want to encrypt, plus the cipher key. You put those two into the box, encryption box, and out spits a cipher, right? Cipher is the encrypted stuff. Sorry, cipher text is the data output, whereas cipher itself is the encryption algorithm, okay? Inverse cipher is just the reverse. Any questions so far? No? Yeah.
And
Oh, right, okay. So Rendell is a cryptographic algorithm specified in this Advanced Encryption Standard, AES. Round keys are derived from the cipher key using the key expansion routine. You remember in DES we also had round keys, right? We had round keys where we had to go through an algorithm to generate each round key. There was a specific method to generate that the round key for each round. I think in DES we had 16 rounds. So the state is the intermediate cipher result that can be pictured as a rectangular array of bytes having 4 rows and NB columns. In this case, we're going to do 128 bits, so we're going to have a 4x4 array. The S box, substitution box, is similar, pretty much the same as the substitution box from the last, all right? It's a non-linear substitution table used in several byte substitution transformations, and in the key expansion routine, you perform a one-for-one substitution of a byte value. It's designed to basically be non-linear. When you do make things non-linear, they're harder to what? Figure out, right? It's hard to figure out. So the substitution box is literally just a table where you go, okay, we have this value, get this value instead. That's all the substitution box or S box is. A word is defined as a group of 32 bits that is treated as a single entity or as an array of 4 bytes. So what is a state? The state, when we say state, we refer to basically, in this case, a 4x4 matrix or a 4x4 array, right? You have a state array, you operate, you put the input bytes in, you have the state array, and you get an output array, okay? So, let's see, 4x4, and all the operations of the algorithm are conducted on the state array, okay? Any other questions? Okay, great. So, for the AES algorithm, the length of the input block and the output block and the state is 128 bits, which means NB equals 4, which reflects the number of 32-bit words in the state. Okay, so for AES 128, you got the key length is a 4, where the block size is 4, number of rounds, right? Remember that number of rounds of that FISO structure? It's not the FISO structure here, but it's the substitution permutation network. There's 10 rounds of that for AES 128. AES 192 has a key length of 6 words, 4 block size, and 12 rounds, whereas AES 256 has double the amount for the length and the number of rounds. Actually, the number of rounds is only 4 more. So that's describing, well, if we have AES 256, how many more rounds do we need to implement? Now, the problem with AES 256 for some embedded systems is as you increase the number of bits for the key, it gets harder to deal with, right? Again, remember, imagine that 8-bit microcontroller having to deal with this. When you double it to AES 256, you increase the amount of work that microcontroller has to do. Think about that microcontroller, if it's living off a little coin cell battery, how much life expectancy does it have if you switch from one encryption algorithm to another, right? So that is a special, basically, thing that you need to take into account when you're dealing with an embedded system. Okay, so the cipher is basically just this. This is just the pseudocode for the cipher. You initialize your state array, you have a state, you get your state input, you have your round key, your add round key, and then for rounds, from step being to 1 to basically 10 for the 4x4, you got your subbytes, shift row, mixed columns, add round key, and you keep going doing that. Then you do your final round. Actually, it's not 10, it's 1 to 9, and the last round has the subbytes, shift rows, and add round key. Because for the last round, you don't do a mixed columns. So for round 1 to 9 on the AES 128, you would do this, and then for round 10, you'd go here because it does not mix columns on the last last round. Okay, so first you add the round key, you just load the plaintext key and XOR it with the state. The state should be loaded with basically the plaintext. So the number of rounds, for number of rounds 10 for AES 128, we have to go through subbytes, shift row, mixed columns, and add round key. We're only on slide 20. It'll take a while. Okay.
You got time.
Huh?
You got time.
Oh, I have time.
You got like 40
I'm only
minutes.
15 minutes in.
Yeah,
Let's get like 40
Thanks.
minutes.
10-minute break, come back.
10-minute break, come back.
Breathe for a moment.
Okay. All right. So for the subbytes transformation, subbytes is basically called nonlinear byte substitution. So what subbytes does is it says I have this input and basically map it to this output. Yes, there's a mathematical description, Gallo field 2 to the 9, calculate it by applying the affine transformation over that. Or essentially what you really just need to do, and I put this on the next slide, is basically use a lookup table. It's basically just substitution. So you take your original and you say, oh, okay, I have to apply the substitution box to get a new value for this. So all you have to do is actually ignore that math part. All we have to do is say, if you have that in that box over there, you have a box S00, and we have the value of 5, 8, right? 5, 8 in that box. We have 5. You have 8. Should have used red. You just substitute that value with 6, 8. That's all the subbyte stuff is doing. That's all it's doing. Okay? We don't have to calculate the multiplicative inverse in that. We just use a substitution table. That's really what it is. Okay, so substitution. The goal of substitution step is to reduce the correlation between the input bits and the output bits at the byte level. The bit scrambling part of the substitution step ensures that the substitution cannot be described in the form of evaluating a simple mathematical function. Again, the subbytes table is designed such that you don't have a linear correspondence, right? You don't have a linear relationship between like the input and the output. Want that linear relationship. So shift rows is the next step. What we need to do when we shift rows is basically shift rows, but we do not shift the first row. So the first row comes over the same, okay? But the second row, you shift 1 over, the The second one, you shift these two over. You basically cyclically shift, and then this.
This one shifts the other way?
What?
Is it shifts the other way?
No,
It doesn't seem.
I don't think. No, it's right. No.
Oh, I think it's only.
It is 3 bytes.
Oh, right. It is. It is. It's just it looked weird. Yeah. So first row, no, don't touch it. Second row, rotate over by 1. Second row, take the 2 and rotate it. Third row, or sorry, the last row, take 3 and rotate it over. That's why 3, 3 is over there now. Okay, so for mixed columns, all you have to do is basically move the entire column over. Okay, so mixed column transformation operates on the state column by column treating each column as a 4-term polynomial as described in section 1.3. The columns are considered polynomials over Galois-Field 2 to the 8 and then multiplied modulo of x to the 4 plus 1 with a fixed polynomial a of x given by the equation below. Okay, well, we don't need to worry about that. Because, well, if you want to understand, what?
You're gonna upset Sapphire.
So last year I got the entire class panicked at all the math. So this year I was like, okay, I'll just get rid of a lot of the math. If you want to go over calculating something in Galois-Field 2 to the 8, multiply modulo that with a big polynomial, you can do that on your own time, but I'm going to go through shortcuts so that we don't have to. I really don't want this class to become bogged down with math. That being said, probably get in trouble for that. Anyway, so as a result of the multiplication, the 4 bytes in the column are replaced by the following over here. So basically, this is always the case. You always use this matrix, and you always multiply it this way. Now, you don't. Let's see here, 2. So S00 over here, S00 prime, becomes this over here. So 2, 3, 1, 0. So it's essentially 2 times this value, 3 times this guy, and then it's S2 XOR S3. Sorry, that's an XOR. Right, so that's an XOR. So let me go over that again because I think that was a little confusing.
Well, you're saying that the S prime is actually it. You're going to move it backwards on for it.
So to get this, so to get S prime 0 comma C, you follow this equation. Since it's in the first row, we use this. So it's a 2 multiplier of 2, 3, a 1, and a 1 over here, which they just omitted, right? And then you multiply by S0 over here, S1 over here, S2 over here, S3 over here. Okay, but that's not exactly it. Because you're doing this multiplication in Galois-Field 2 to the 8, which means you have to do it a little differently. If it's not on the next slide or so, there's an example. So the next one is an add round key. Add round key XORs each column of the state with a word from the key schedule. Okay, so add round key. In the add round key transformation, a round key is added to the state by a simple bitwise XOR operation. So you remember that earlier thing, that 44 generated values. You're using 4 of them, XORing it with the current state array, the current value of the array. So, yeah, that's all it's doing. Okay, so the last round. Again, for the last round, the 10th round, right? In AES 128, we got 1 to 9, then we got 10th round over here. We are not going to do the mixed columns, which is why it's broken out over here, okay? So for decryption, it's almost the same thing in reverse. It's almost the same thing in reverse. So let's see, we have the state, at the input array, we do the add round key for, let's see, so now it's 9 down to 1, and and this one's the last one. I'm guessing it's 0 indexed. So for round 9 down to 9 down to 1, we're going to go through inverse shift rows, inverse subbytes, add round key, and inverse mixed columns. Then we're going to go and do the inverse shift row and inverse shift subbytes and add round key without the inverse mixed columns for the last round. Any questions so far? Any questions? No? No one lost?
Many, but I don't really know how to ask them.
Wait, so
What is your question?
He just told me.
Well, I'm still just trying to get the all of the permutations in my head here, and that's, I think, is over relating a little bit.
Okay, where are you still working on?
it's called? It's great.
Where are you trying to still work it in your head? Which step are you at?
Well, okay, so I see that we have to do these lookup tables, which essentially are just generated off of XOR math already for us. So we
So
turn around and
you
just look them up.
so you get subbytes, right? That's the one where you just look it up.
Yeah.
Okay. After subbytes, we got the shift rows where we just rotate the rows around, right?
Right, and each row is rotated slightly more than the previous row.
Correct. Where the first one is not rotated at all. The second row is rotated by 1, 2, and then 3. And then you get 3, 0 over here, 2, 0 over here, 1, 0 over here. Okay? Do you follow that?
Yes.
Okay. Then we're at the mixed column step. Is this where you're getting lost?
And you take one entire column that's treated as one giant vector.
Correct. So we treat that as a vector, and we plug it into this, right, to generate the new column. We generate the new column. This array over here is fixed. This is your input column. This is your input column. And this is your output column that's going to replace that input column. So we do it one column at a time for this mixed column step, okay?
Okay.
And in order to mix columns, what we're doing is we're doing math over here, S prime 0C. We basically, because this is the first value, S0 prime C, we take the first row, which is 2, 3, 1, 1. So it's a coefficient of 2, coefficient of 3, coefficient of 1, coefficient of 1. And we multiply it by this guy over here. Oh, sorry, that's not that guy. So this guy comes, let me use another color. This guy comes from over here. This guy comes from over here. This over here, and this over here. Okay?
All right.
And that's basically how we get S0, S prime 0C, S1 prime C, S2 prime C, S3 prime C. Okay?
And that array is an established array. That's not something that we get from the actual message or the key. That's just always that way.
Yep, it's part of the algorithm. We treat it as part of the algorithm.
So that arrays used to
Okay.
Right. That's the doc?
So basically, the way to make the array is literally it's matrix multiplication, so it's like row times column.
Yes.
Yes,
What it is.
except this is not multiplication over here.
Instead of multiplication, that's XOR.
This is XOR, but it's also XOR in Galofield 2 to the 8, which is a little different.
What's
I'll
this
mention-
solid?
What?
What's this solid dot there? Is that one actually
It's
multiplication?
actually just multiplication.
That's the multiplication.
Okay. So
But
it's
it's
from XOR,
multiplication in Galofield
but 8.
Gotcha.
2 to the 8.
Gotcha. Yeah.
Okay, so we're at add round key, right? We're going to export each column of the state with a word from the key schedule. The key schedule was generated per round, right? We had those generated, and we're just going to XOR, right? Okay, just going to XOR. And again, when we get to the last round, of the algorithm, we don't do the mixed column step because we don't need to. So decryption is almost the same in reverse. Again, the last round decrypting, we do not need the mixed column step. And okay, so here's an actual cipher example. So what we go through here is we start over here with the input array. The input array is loaded with just the plain text input over here, right? This goes in here. And then the cipher key over here, initially the first round just gets this. Now the second round, or this round over here, is generated from a key. We're generating it from a predefined algorithm to generate the key. Right? That's just coming from something else. So input, the starter round, then we do a substitution step, the subbytes with the subbytes array, or basically lookup table. Then we do a shift row step over here, and then we do mixed columns. We XOR it with a round key value, and then we go to the next round over here for the starter round. Okay? So everyone follow that. We start the algorithm by having the input array. We have the round key value being the initial cipher key, and we basically do start a round. We do a subbytes with that array. We do shift rows where we rotate the rows around. We mix columns by using that multiplication that of each row in the matrix, right? And then we XOR it with a round key value, giving us the next key, the next state. And we do that 10 times. Okay? Yes?
So the GF, that stands for Gallo font, you say?
Field.
What?
Field.
Gallo?
Yes.
Field.
Field.
So
Field as
that's
in
just a
field hockey.
modulus operation?
I believe so.
You,
Not sure.
so you just take the lower 3 bits?
I have it on the slide, and I'll show you how to do it in a minute. It's not just taking the lowest 3 bits, though. It's not. I believe you XOR it with something else instead, and then you. We'll get to that in a minute. Okay. So cipher example. So we're starting a round over here. After subbytes, we get here because when we're doing our subbytes, we have 1, 9, right? So we got 1 over here, 9 over here. We're going to sub it with D4. We got 3D over here, so 3. And D is over here. We got 2, 7. We got, let's say, 8D. 8D becomes 5D. So 8D becomes 5D. Okay? You guys follow me with the subbyte step? Okay, good. Then we're going to go to the shift row step. Again, first row gets left alone. Okay, so second row, rotate over here 1 by 1. Second row, rotate by 2. Third row, rotate by 3. Move them over. Right? Does everyone follow that? Yes? Okay. So after shift rows, after mixed columns, okay, this is going to get a little harder. Okay. So to get 0, 4, you do the following. Okay, you follow this equation. Basically following this matrix again. But I don't expect you to get it like that, so let's see here. D4BF5D30. That's the column, right? D4BF5D30. Okay, you plug it into that equation. Now, DFBF5D30. Then we multiply by this known entity over here, 2, 3, 1, 1. So 2, 3, 1, 1. Actually, these should be XORed, actually. So those should be circled, actually. That's wrong. So that's how we set it up. Does everyone follow how we set it up so far? Okay, so we're left with this equation over here. S prime 0C for that spot is 2 times D4, XOR 3 times BF, XOR 1 times 5D, XOR 1 times 30. So you eliminate the 1 off the bat. It's just 5D and 30. Okay. multiplication must be done in Gallo if you have 2 to the 8. So what you do is this 2 times d4 turns into d4 shifted over by 1 is 1a8. The MSB is set. If the MSB is set, we XOR it with 1b, and we get 1b3 where we ignore the 1, so we get a b3. That becomes what? It becomes b3 instead of that 1a8 in the final equation. The other thing we need to multiply is the 3 times bf. So the 3 times bf turns into bf shifted over by 1 is equal to 17e. Since the MSB is set, we XOR it with 1b. We just use 1b. Okay. We just XOR it with 1b and XOR it also with bf again, since it's a multiply by 3. Right? Because if you shift it over by 1, you're just multiplying by basically 2. Right? Okay, so once you multiply it with 1b and bf, we get 1dA, we ignore the 1, and we're left with the dA. So b3 XOR dA XOR 5d XOR 3, 0 gives you 0, 4. Yes?
Okay, so I see why you multiplied it by 3, but then you rather below that you just multiplied by 2.
That's a multiplication by 2, but we're XORing, oh.
You didn't multiply that by, what is it, 1a, no, d4? Sorry, XOR that with d4, the first one?
Well, look, wait. Before that,
Hold on. Which one are you describing here? We're describing 2
I'm
different
talking about the top right.
You're talking about the top right.
How 3 times bf turns into bf shifted over 1.
Right. We get 17e. And since the MSB is set, right, with 1.
Oh, the MSB is set. That's
So we multiply it with 1b by default. We just do that. And then we XOR it itself again with a. We XOR itself with itself. That is just how I'm going to describe it. That's how you get to the correct answer. That's what I'm going to try to leave it at. Yeah.
So why didn't we do that in the first case?
Okay. Because it was a multiply by 2.
So,
Okay.
Right.
is it odd even? Is that determined?
Is that
I
how that
think
works?
it's just 2 you don't, and 3 you do.
What about
1?
1 you just leave it alone. 1 just goes away. See, so I was gonna write on that board. So this 1 over here goes away. See?
yeah?
Okay. The 2 you need to do a shift left, and then if the MSB is set, you XOR with 1b. If it's not set, you would just leave it, and then you get the result and ignore the 1. For the 3 times bf, you get bf shifted over by 1, you get this value over here. The MSB is set, we multiply it, we XOR it with 1b and XOR it with bf since it's multiplied by 3. So we get this value over here and we ignore the 1, and then we XOR all of them together getting 0, 4. Yes?
So what if it's like 4? 4 times something.
It's never 4.
It's just 1, 2, 3.
Okay?
0, okay, gotcha.
So
Gotcha.
again, I'm trying to just give you the math you need to do for this class. It's just like how I tried to do the 2 by 2 matrix with what was the encryption algorithm?
Hell
Huh?
no.
Cipher. Yeah, it was technically supposed to be 3 by 3 or above, but we simplified the math. So you really want to sit there calculating the eigenvector and eigenvalue for a 4 by 4 matrix. And I don't think so. So let's say you didn't get that. Let's do this one. We're doing the same column, or sorry, we're doing the next row over. Sorry, next column over. E4, B4, 5, 2, AE comes from here. You get this equation over here. Because we're on the second row, second column, we're going to use this one. 1, 2, 3, 1. Notice how we used 2, 3, 1, 1 before because we were in the first column. First column, use first row. Second column, use second row. Second row is 1, 2, 3, 1. So 1, 2, 3, 1. Okay? Now we're left with that's wrong. Okay, so 1 times E0 XOR with 2 times E4. Okay, so the easy one to do is just this one. Anything times 1 becomes itself. Multiplication has to be done in yellow field 2 to the 8. So 2 times B4, same method as before. B4 shifted over by 1, left shift by 1, gets you 168. 168 has the MSB set as a 1, so 1 XOR it with a B, 1B. We get 173 and ignore the 1, getting the value 73. So that's 73. So that becomes 73 over here. So 3 times 52 turns into 52 shifted over by 1 gets you a 4. MSB is not set. Do not basically XOR with 1B. But we still need to XOR it with 52. So A4 XOR 52 equals F6, right? So this becomes F6. So again, the MSB being set or not set determines whether you XOR it with 1B, but since this is the 3 over here, you do need to XOR with the value itself again, 52. That's a typo on the slide. It should not be B something, it should be 52 over there. So A4 XOR 52 equals F6. You get to this step, you exclusive OR them all together, and you get CB. Okay? Do you guys follow that? Close enough? Again, I'm trying to abstract away some of the math, so it might seem missing to you, but just follow the steps. Okay? If you want to go look at yellow field math into the 8, you might guess, but I don't have enough time. Okay. Did we get CB? Okay, yes, we did get CB. Good. So round key add. XOR the round key with the next column outputs. So after that, we get 04A4. So 04A4 is just A4. Sorry, 04A0 is A4. So 04 XORed with A0 is A4. Let's see, what's the next one? 4C XORed with 05 is 49. You're just XORing the entire array with the element in the same position. That one's straightforward, right? Okay. Oh man, I keep repeating. The number of rounds required for your AES implementation. In this case, we're doing a 4x4, so you need what? After that initial round, you need 9 more, right? Remembering that the last round does not take the mixed column step. Okay, so round 2. Round 2, we're given this round 2 comes from the output of round 1, right? Then we go through and sub bytes again, then we go through shift rows again, and then mixed columns again with that yellow field arithmetic. We XOR with the key value, right? Each spot over here gets XORed, and then we go and put that in as the state matrix to begin the next round. Again, at the start of round, we get A4, we're going to look up A, and then 4 over here gives you 49 in the table. Over here we have 5B, so we're going to do 5, and then B is 7F. Is it 7F? That's not right. Am I off by 1?
Yeah, go up 1.
So 5B. So 5.
Should be 39.
Yep, it's 39. Thank you. And then something like EA would be E, A, turn into 87, so that's correct. So shift rows, right? First row gets left alone, second row gets rotated by 1, third row gets rotated by 2, final row gets rotated by 3. Okay, that's pretty straightforward. Now, we have to do the mixed column step again, which you guys apparently don't like, some of you. So,
What's going on?
nothing. So 49db873b, we're in the first row, first column. We're in the first column. So if we're in the first column, we use the first row of this predetermined matrix. So we have 2, 3, 1, 1 is a coefficient. We have 2, 3, 1, 1 here. Then we put the 4, 9 over here, db over here, 8, 7 over here, 3b over here. 1 goes away, so it's 8, 7. Again, these are XORs, not pluses. 3b. Then we need to do the multiplication for these two items. So with these two items, we get 4, 9. So 2 times 49. We left shift by 1, we get 092. Since the MSB is not set, we get a 092. We do not XOR, so we get a 92. For 3 times dB over here, when we bring it over here, we shift it left by 1, we get 1B6. 1B6, the MSB is set. XOR with 1B because the MSB is set, and we XOR with dB since it's a multiply by 3. You just need to remember that. Okay, so we get 1B, we ignore the ones. So B6 times XOR 1B, XOR dB is 176.
I think you.
Oh, sorry.
You don't ignore the one here. No. You ignore the one at the end.
Right, yeah. So you're off with that. So let me go over that again because I skipped to this one by mistake when I was thinking. So we're left with dB, left shift by 1 is 1B6. 1B6 XORed with 1B because the MSB is set. And we XORed with dB because it's a multiply by 3. We get 176. Ignore the 1 to get 76. We get the 92 coming over here, and we get the 76 over here. XORing with the remaining 8, 7, and 3B gives you a 5, 8. Okay? You guys follow that?
So it's always 1B.
Yes, always by 1B. Exactly. Yes. Do we want to go over this again?
No.
No?
No.
You sure?
I like set mine up for like way far in the future. Then we have any.
Okay, so I'll just skip ahead if that's okay with everyone.
Yes.
Okay. Cipher key, round key add. So again, the last step, the round key add, is just XORing all the elements with the elements in the same spot. And you get this over here, which you use for your next round. Okay, so we keep going, use a computer for this step, and then we get the final output. Right? So this is your final cipher text output from the cipher algorithm itself. Any questions so far? Yes, no? Okay.
No, I actually have a lot less questions now. I'm feeling a lot better about this.
That's good. Okay, so key expansion, key schedule needs to be generated for each round. Basically, you go through an algorithm to generate the key. You go through this algorithm. I don't really want to go through it. I'm not going to ask you on it. But you basically follow this algorithm to generate that 44 bytes worth of values, where you use 4 of those at a time in the key, the key for each round. Okay? That's where the key for each round comes from. So if we go back here and we have this round key that we XOR with, it is coming from this key expansion algorithm that is described here, which I don't feel the need to go into detail on, and I won't ask questions on it. Okay? Most I'll probably ask is where does it come from, and you can just say key expansion algorithm. Okay, so, yeah, we don't need to go through this. Okay, so there's something called ECD and CDC mode. So one thing that you need to notice is, okay, we have AES 128 works on 128 bits, which is how many bytes? 16 bytes of data, right? If it's 16 bytes of data, if you have more than 16 bytes of data, what happens? You have to run it over again, right? So what happens, that's called electronic codebook mode, right? So that's where you have this round 1, so you have, let's say, 48 bits total. 48 bits total. You use the first 16 bits over here, you use 16 bits over here, and then you use 16 bits over here, right? You just give me the plain text, split up the plain text into 16 byte increments, run it with the key, and get the ciphertext output. Okay. Now that should not be used. We're going to use it in this class because it's easy to deal with. The code mode, this mode is weak because of plain text taken 128 bytes at a time and encrypted with each key is not a good thing. Okay? Not good at all. Right? And I'll tell you why. But the thing with this mode is it can work in parallel, which is kind of nice. You can set this up to run in parallel. It takes way less resources. You can parallelize it on FPGA. But this is the problem. So encrypting with ECB leaves residual information. So when you do that, when you encrypt 16 at a time with the same key, you have this image you encrypted, you're left with a residual. You're left with a residual using ECB mode. Now, if you use something other than ECB, like CBC, which I'll describe on the next slide, you get an image like this, which is, it doesn't give it away, right? So ECB mode, when you take it 16 bytes at a time, it does give you residual information. So CBC mode is basically cipher block chaining, where you have an initialization vector over here, just a random value, right? And you use this initialization vector to XOR with a plain text to hide it, and then you run it through an encryption key. Now, what happens is the subsequent block, you take the output of the ciphertext, export it with the plain text to hide it, right? And then for this one, this next one, you take the output of that, XOR it with the plain text of the input for the next encryption, so that you hide it. That way, you don't end up with something like this image here, right? If you don't use CBC mode or something else, like an initialization vector in CBC mode, you will be left with that residual image, which is not necessarily good. Okay? And I think that's all I'm going to cover for today. Okay?
CBC mode takes a lot more time.
CBC mode does take a little bit more time. And the other thing that you have to watch out for is with CBC mode, you have to wait until the previous cycle is done in order to get the ciphertext to XOR with the plain text with the next round, right? So it might be, this is slow. Pipeline. That's your pipeline. All right, so no more questions. Is there any more questions? No? There's none. I'll see you on Friday. Remember, what? Was there a question?
I just have one, yeah.
What is
Sorry,
it?
Stephen again. Just like the 2, 3, 1, 1 block, the giant lookup table for the substitution box, is that always the same, or is that generated before you begin?
It's always the same. It's always the same.
It's always the same.
Now,
Okay, cool.
remember that you need to get your quiz into me before Friday at 3 p.m. or you will get 0. Okay? I will see you guys on Friday.
See you Friday.
I was gonna slowly move my hand.